Welcome everyone to the first Food Science Seminar Spotlight for 2024. I hope you've all had lovely summer so far and that the sunny weather lasts a little longer where you are. Tēnā koutou katoa, ko Ingarani me Piripini te whakapaparangi mai, ko Lester me Bristol te whenua tupu, ko Tamaki Makoro te Kainga, he Industry Research Liaison Manager o i New Zealand Food Safety Science and Research Centre, ko Kyla Archer toku ingoa, tēnā koutou katoa. So today we have a speaker for you who is currently a little far from home. Professor Eric Decker is a professor in the Department of Food Science at the University of Massachusetts Amherst, which is also the largest Department of Food Science in the US, and is currently visiting the Coldfront Institute. Eric is actively conducting research to characterize mechanisms of lipid oxidation, antioxidant protection of foods, and the health implications of bioactive lipids. He has over 460 publications, and he has been listed as one of the most highly cited scientists in agriculture since 2005. So Eric will be talking to us today about lipid oxidation, methods of control, and potential toxicity. He's in New Zealand visiting for the next 3 months on sabbatical and is also keen to engage with our wider colleagues that are all attending today. So thank you for taking the time to present to us today, Eric. We will have some time for Q&As after the presentation, and Matt will also be joining from the Coldfront Institute to kind of set what Eric talks about within the New Zealand perspective. So if you have any questions, please put them in the Q&A box at the bottom. But otherwise, Eric, it's over to you.
Thank you so much, Kyla. So let me hope the share works like it does when you practice. All right. Okay, so thanks for having me. We're really enjoying our time in New Zealand. Weather's been awesome, and we get 2 summers this year, so we're kind of feeling very spoiled. But there is some work that's going on too, and I'm more than happy to talk to you guys, and please feel free to answer questions or even contact me later if you would like to. So just a little background on lipid oxidation in general. So, the reason we worry about lipid oxidation in foods is because it really is one of the major chemical pathways of food spoilage. And this occurs mostly because it causes a whole host of molecules that cause off flavors. And this leads to food waste and is the limiting factor in the shelf life of many food products. But lipid oxidation is also a problem. So it will also co-oxidize other food components. And so it's one of the main reasons that you can lose vitamins like vitamin C and vitamin E. And then, as I'll just briefly mention later, there's also a whole host of different toxic compounds that are formed by these pathways. So we need to be worried about control and exposing the population to food products that are rancid. So there's been several challenges lately because the oxidative stability of food is decreasing for several different reasons. One is that's happening in the US, and I think it's happening worldwide, is the removal of partially hydrogenated fats from the food system. And this is to minimize the amount of trans that are in foods. This partial hydrogenation was a big strategy to control oxidation because it gets rid of double bonds and helps stabilize things like soybean oil. We're also seeing a lot of sustainable packaging. In this packaging, a lot of the ways that they make it sustainable is that they make it lighter, they make it less thick plastic, for instance. And when they do this, the oxygen permeability goes up. And then we also have this desire to allow consumers to see the product, which means that that product gets exposed to light, which is another factor that increases oxidation. There's also a lot of trends to incorporate nutritionally beneficial lipids, so say omega-3 fatty acids, and these are very, very susceptible to oxidation. And then the clean label demands of consumers to get rid of synthetic food additives as a whole, but this includes the synthetic antioxidants, which can be sometimes the most effective antioxidants in the food system. So now, the reason lipid oxidation impacts flavor is because the reaction results in the breaking down of the fatty acid molecule. So if you think about it, a triacylglycerol should not smell because it's not volatile. And for that matter, a fatty acid is also not volatile and doesn't create a smell. So it's when that fatty acid oxidizes, it breaks down into small molecules that are volatile, and these molecules are what causes rancidity. So go home tonight, smell your oil, not your olive oil, just your regular vegetable oil or your canola oil. And if it smells, it's rancid. If it's fresh, it should have no smell at all. Now, the molecules that are formed are generally negative, but there are some instances where they can be positive as well. So here's some of the descriptors that people have used for these. Hexanal, very common byproduct of oxidation in omega-6 fatty acids. Another one that comes from omega-6 fatty acids is this 2,4-decadienal. It actually is the flavor that we associate with fried food. So fried food, a little oxidation is actually what creates the flavor. And then when we look down here at these unsaturated aldehydes that you get from fish oil, these are very strongly negative oxidation smells. Now, of course, oxidation or flavor is a function of the fatty acid type. So each fatty acid produces different molecules, different oxidation products, and those different oxidation products can smell differently, like I just mentioned. They can be produced in different quantities, like hexanal would be a major one, 2,4-decadienal may not be as much. And then these volatiles have different sensory levels. So the ability to smell those volatiles is really a combination of how much is in the oil and what their sensory threshold is. So you can see here something like hexanal. You can start to smell hexanal at 150 parts per 150 parts per billion. But then when we get down here to these unsaturated aldehydes that come from fish oil, the sensory threshold of these can be 1 part per billion. So you can, even when you're dealing with fish oil or a fish oil fortified food, very, very small amounts of oxidation can be detected by your nose. Your nose is actually more sensitive than most mass specs. So this is not only a challenge to stabilize the fat, but if any oxidation occurs at all, or you have an oil that's not absolutely pure when you start, you're going to have fishy off flavors. And then also that we also have the risk of toxicity of these products. This slide over here on the left shows 2 oils that were produced in the lab where we had an unoxidized corn oil and then one we allowed to oxidize. This dotted line on the top here is the recommended industrial level of peroxide. So anything under a peroxide value less than 10, it's considered an okay oil. But when we took these 2 oils and we put them into colon inflammation model system, a colitis model system, you can see that oxidized oil caused a lot of weight loss in those animals, and it basically caused a lot of issues in their gut, increased gut permeability, damage to the microbiome, and so on. So they do seem to be something of potentially a great health risk, especially for anybody that has things like inflammatory bowel disease. Now, we've known about oxidation for over 100 years. We still haven't solved the problem, and part of that is just because there's so many different things that impact lipid oxidation reactions. How unsaturated your fatty acids are, the pro-oxidants that are in the system, the antioxidants that are in the system, and both in the lipid phase and the aqueous phase, because remember, much of our food is going to be lipids dispersed into water phases. And then when you have these kind of complex systems, you're going to have an interface between the lipid and water, and the properties of that interface can also impact oxidation. So there's so many different things that impact. It's really, really hard to come up with a single solution that will apply across all food systems. So I wanted to talk a little bit today about tocopherols and the role of tocopherols in this. And I decided to do this as I was putting the talk together because I know we have a pretty diverse audience here that works in different food systems. And tocopherols are probably the one antioxidant that crosses all food systems. And the reason for this is that tocopherols are produced by all plants. So any plant oil that you would get can naturally contain tocopherols in it. But on the other side, it's an essential nutrient for animals. So both in dairy and meat products, you're going to find tocopherol, but that tocopherol is going to come from the diet of the animal. The reason that we have tocopherol, the reason it's so important in our body is that it stops lipid oxidation in the cell membrane. This is the molecule here, and it has this big phytol chain that lets it anchor itself in the cell membrane and becomes a very effective antioxidant. In our body, this tocopherol works together with vitamin C to create a very antioxidant environment and prevent the oxidative degradation of our cells. When we go out and look at the tocopherols, there's actually 4 different homologs: alpha, beta, gamma, and delta. And there's also in some, especially in the tropical oils, you'll find tocotrienols. And this is where the phytol chain is unsaturated. So it has the same homolog forms. These homolog forms are different variations of how much this phenol ring is methylated. And that also impacts their polarity, with alpha tocopherol being the most nonpolar and delta tocopherol being the most polar. Now, the way tocopherol works, any free radical scavenger works, is that it's able to interact with a fatty acid radical. So for instance, it can interact with this peroxy radical here. And when it does that, the radical from the fatty acid transfers to the antioxidant. And then the antioxidant can distribute that radical throughout the phenol chain, which lowers its energy and prevents the antioxidant radical from having enough energy to oxidize a fatty acid radical. But the downside is that antioxidant is consumed during this reaction. So eventually what happens is that the antioxidant is all lost and the fatty acids start to oxidize. So the way to think about this is antioxidants are preferentially oxidized. They oxidize much faster than the fatty acid. And it's not until the antioxidants that are gone till the fatty acids start to oxidize. So just a little bit about the in vivo world of tocopherol, because there is very specific metabolic pathways by which and bioavailability factors by which it comes into our body. So if you eat any kind of plant source which have tocopherols, it's going to have all the homologs in there. And all those homologs are going to go from your gut into chylomicrons, and they're going to go to the liver. But once they get to the liver, only alpha tocopherol makes it out into VLDL. And the reason for this is that in your liver, there's a tocopherol binding protein, which has very strong preference for alpha. And so the rest, the gamma, the delta, and the beta, never make it into the VLDL and never get to your peripheral tissue. And so those homologs are just excreted. So you will see dietary supplements which have all the different tocopherol homologs in it, but you're really just excreting those other homologs if you take these kind of supplements. So there's lots of evidence that people don't consume enough alpha tocopherol for optimal health. But on the other side of this, it's very, very rare to have deficiency issues. Most likely the people that have deficiencies are people that have problems with fat absorption. So there is benefits to eating more alpha tocopherol, but we almost never see a deficiency system. And the benefits are mostly around inflammatory diseases like heart disease. So as food scientists and as people that are trying to protect our foods, we can go out and buy both alpha and mixed tocopherols as food additives. Mixed tocopherols are, as they're named, they're a mixture of all the 4 homologs of tocopherols. They're a byproduct of the deodorization step of refining. and you can get different ratios of the different homologs depending on the raw material. So mixed tocopherols from soybean will be slightly different than mixed tocopherols from canola or mixed tocopherols from sunflower, for instance. As a food additive, the mixed tocopherols are generally better than alpha. And this just shows some work in an emulsion system. And you can see that the controls on the top, and then alpha does inhibit oxidation, but doesn't inhibit it as well as the mixed tocopherol. And the theory here is that the mixture of tocopherols allows them to get distributed more evenly throughout the food system. So tocopherols are probably overall the most important antioxidants in the food system. And this is just because they're so widely distributed. It would probably be very few food products that would not have at least some tocopherols in them. And these tocopherols that are in there just provide some inherent stability to the product. So a lot of times you'll hear people talk about, well, I cooked some bacon, and that bacon's going to be oxidized by the time it cooks. Well, that's not really true, because there's some tocopherols in there that are going to prevent oxidation for a period of time, and until they're completely consumed, the oxidation won't occur. So all foods have some inherent oxidative stability from tocopherols, and potentially other antioxidants as well. Those tocopherol concentrations vary greatly in different foods. In some cases, like when we refine oils, the refining steps actually take some of the tocopherols out. Some food processing operations, like extruding, problem in pet food is when they extrude pet food and the steam comes out once the product goes through the dye. That steam actually distills a lot of tocopherols out of the product. So there's some food processing operations that could remove them, or maybe cause some processing operations that cause oxidative stress and degrade them. And then in animal products, the tocopherol levels are very diet dependent. So if you supplement an animal with tocopherols, you can quite dramatically change the amount of tocopherols in there, and that also then their inherent oxidative stability. So varying the concentrations can be an effective way. So there's going to be some food systems where if you add more tocopherols, you'll get additional protection. But the problem is that if that tocopherol gets too high, then they can become pro-oxidant. Tocopherols, like all antioxidants, are reducing agents. And if their concentrations are too high, they can reduce metals. And that metal reduction can actually make the oxidation go faster. So in something like soybean oil, the naturally occurring tocopherol levels in soybean oil are actually too high. So when they refine the soybean oils, they strip some of that tocopherol out, and then they add it back to the optimum level. And then this is an advantage for the refining industry, because that excess tocopherols they can sell as dietary supplements or feed additives. So you can really only get so much protection from tocopherol alone. You can't just keep adding it and getting better and better protection. There's going to be a maximum protection. And the problem that you have is once you have that oxidation starting, the tocopherol concentrations are starting to go down and you're losing tocopherols. But there is an ability to reduce those tocopherol back by other antioxidants or other compounds to regenerate them so that they maintain their activity for a long time. We do this in our body. As I mentioned, vitamin C, ascorbic acid, is very important in this. But this can also occur with other food additives. And this can result in synergistic activity, which can greatly enhance tocopherol's activity. This is the pathway that it happens in your body. So if we have a fatty acid, a lipid radical that forms, it's scavenged by the tocopherol, and it's converted to this tocopherol radical, is tocopherol quinone, and then ascorbic acid reduce it, can come back to its original NADH system, can reproduce the ascorbic acid. So we've been doing some work lately on this type of interaction with phospholipids. So phospholipids actually aren't reductants, but they have the ability to bind to this tocopherol quinone and donate an electron to regenerate it back to alpha tocopherol. So you can see this is an experiment where we actually mix together the tocopherol quinone and either DOPC, which is phosphatidylcholine, or the phosphatidylethylamine, or ethanolamine by itself. And you can see that the phosphatidylethylamine and the ethanolamine convert that quinone back to the tocopherol, back to the alpha tocopherol. Whereas phosphatidylcholine doesn't do anything. It doesn't have the ability to regenerate the tocopherol. So when we look, the other phospholipid which will also regenerate the tocopherol is phosphatidylserine. So this is an experiment in emulsions. Here's the control. These two are the phospholipid by itself. And then this is mixed tocopherol. So you can see the mixed tocopherol was effective. This is a case where we stripped out the tocopherols in the beginning and then added the tocopherol back. The tocopherols extended the lag phase by 2 days. But then when we added a combination of phosphatidylethylamine or phosphatidylserine, you can see that we got an extension of oxidation, even though the PS and the PE can't inhibit oxidation very much by themselves. So this is a synergistic interaction. This also works in bulk oil. Here's bulk oil with phosphatidylethylamine. So you can see the PE doesn't do anything by itself. The tocopherol alone, and then the combination again, we get another 7-8 days of lag phase when we use the combination. So this is very promising, but the problem is that when we go look at lecithins, PE is usually not the major component in lecithins, and usually it's PC. And remember, PC doesn't do this regeneration. So we developed a system where we can take phosphatidylipase and we can react that with phosphatidylcholine. And if we put either ethanolamine or serine in there, this will produce, this will convert the PC into the PE or the PS. And here's an example. Here's egg lecithin, originally 70% PC and 14% PE. And after reaction with the phospholipase D, we can get 94% PE. And then when we look at those again in either our emulsion system, again, the lecithins by themselves do very little. And then if we mix the combination of the modified lecithin with tocopherol, we get again a synergistic increase in lag phase. And then this is bulk oil. Sorry, a lot of stuff on this slide. But really, again, the story is here's tocopherols by themselves. Here's all the phospholipids by themselves. And here's the combination of tocopherol and the phospholipids, again, showing synergistic activity. And then finally, we can also add these to I think this was a soybean oil, and utilize the tocopherols that are naturally occurring in the soybean oil. So here we don't add any tocopherols, we just add the modified lecithin. And that modified lecithin can then regenerate the tocopherols that are already in the oil. And here you can see an extension of lag phase of about 8-9 days. So again, producing synergistic activity. So tocopherols will also interact with phenolic compounds, and these interactions can be both positive and negative. So synergistic activity usually happens when the phenolic antioxidant is able to regenerate the oxidized tocopherol, similar to what I just showed you with the phospholipids. But the problem with some of these antioxidants is that they can actually reduce metals. And whenever you have a situation where a metal gets reduced, the reduced metal is much stronger pro-oxidant than the oxidized metal. So anything with a very low reduction potential can turn into a prooxidant. So this shows you an example of that. So here you look at the reduction potential. So this is the reduction potential of a fatty acid, polyunsaturated fatty acid radical. So any molecule underneath this potentially can quench that polyunsaturated radical and stop oxidation. But the problem is if you have molecules that are below this reduction potential, which is the change of iron from +3 to +2, they can be a prooxidant because the antioxidant can convert the +3 to +2, and it's the +2 that really generates the free radicals. So this graph over here shows that you can have situations where we have ascorbic acid or things like catechins from green tea, and they can actually become prooxidants. So even though we think of them as antioxidants, if they do this iron reduction, they can turn into prooxidants. So the other advantage of these low reduction potentials is if they can regenerate tocopherols. So if we look at something like this catechin, which I just mentioned, can reduce iron, its reduction potential is above tocopherol, so it cannot reduce tocopherol. But if we look for phenolic compounds, and ascorbic acid is another example here, that have lower reduction potentials than tocopherol, these have the potential to regenerate oxidized tocopherol. So Ipek is a postdoc in my lab, and she's done a lot of work on this. Again, here's a control. Here's the tocopherol alone. Here's myristotin alone. And then here's the combination. So you can see a huge synergistic interaction with this myristotin tocopherol. And then this is in an emulsion, even more, right? So here we went from a lag phase. Lag phase is really the best indicator of the shelf life of the food. So here's say a shelf life of 7 days that can be extended to 30 days by this combination of myristotin and tocopherols. However, if we take the same emulsion and we decrease the pH to 4, things change a little bit. The myristotin by itself still works some. Out here, the tocopherol works pretty well at that pH, but if you have the combination of tocopherol and myristotin, it actually ends up being worse than tocopherol by itself. So this is an antagonistic now. Now the myristotin is being a prooxidant or causing prooxidant activity. And this is what I mentioned before, right? Because it has such a low reduction potential, it can be very powerful at reducing the metal. And that reduction of metal tends to get stronger at low pH. So you can see at pH 7, there's not really a lot of metal reduction. But if we go up to down to pH 4, now the myristotin starts to reduce the metals. So most likely the reason that the myristotin doesn't work at pH 4 is because of this metal reduction. So it's really both being an antioxidant and a prooxidant at the same time. And as pH goes down, its prooxidant activity increases. So this is a huge problem. A lot of our food products that really have oxidation problems are at lower pHs, like salad dressings and mayonnaises. So it's very hard to find good antioxidant solutions at that pH, which is why EDTA still is on the marketplace. So just to switch directions a little bit, in meats have lots of oxidation problems themselves. And you would think that in some meats that they really wouldn't have too much of a problem with oxidation because they're quite saturated. So if you think like lamb and beef, very high in saturated fats, and you would think not a lot of oxidation. But the problem is in meats, most of the oxidation occurs in the cell membrane. And there's two reasons for this. One is that the cell membrane has this huge surface area, which allows interactions with prooxidants like iron, right? Because meat has a lot of iron in it. But also biologically, to keep this membrane fluid and functional, it has to have a lot of unsaturation. So even though a meat overall might be quite saturated, the cell membrane will still be quite unsaturated. Oops, sorry. This shows some work all the way back from my PhD days where we looked at mackerel, or I'm sorry, we looked at herring in this case. And what we did is we monitored the DHA, so this is the omega-3 fatty acid to stearic acid ratio. And as that ratio drops, that means the number of unsaturated fatty acids are going down. And if we did that this is the sarcoplasma reticulum, so this is a cell membrane. And so you can see when the cell membrane goes along, all of a sudden its unsaturated fatty acid concentrations go down. So there's oxidation occurring in the membrane. And then this is MDA, which is a TBA product. And it goes up about the same time that the membrane fatty acids go down. Whereas if we check the triglyceride fraction in here, you see no change in fatty acid composition. So this and several other papers have shown quite strongly that it's really the membrane that we need to worry about. So if we want to then protect the meat, we not only need to add an antioxidant, which can be effective, but we need to get the antioxidant into the cell membrane. Because if all the reactions occurring in the cell membrane, we want our antioxidant to be where the free radicals are being generated. Now, a lot of times, if you buy antioxidants, they don't come as the pure antioxidant. They often come in an oil, like just in a regular vegetable oil or maybe a medium chain triglyceride oil. And if you take that antioxidant, this is a case where they use delta tocopherol, and the reason they pick delta is not normally in the fish tissue, so they could determine exactly how much tocopherol got in the membrane. And if they took the delta tocopherol and they put it in oil, you can see only 28% of it ended up in the oil, and the rest of it ended up in the triglyceride fraction. Whereas if you use ethanol as the solvent, a less polar antioxidant, a less polar carrier, you're able to get more of the antioxidant in the membrane. And this is a similar, except in this case, they use BHT, which is a very non-polar synthetic antioxidant. If they put it into the haddock using an oil carrier, they got some protection, but if they put it in using the ethanol carrier, they got much better protection. So if you're trying to add antioxidants into the meat system, you really want to try to use a more polar carrier for your antioxidant to try to get it in the membrane. Now, the other thing about meat is that if we have this tendency to take these very non-polar tocopherols and we put them in meat, like in the previous experiments, that fish was pretty lean, not a lot of triglyceride. But if we put them in things like pork and beef and turkey, these got really quite high fat contents. And if we put alpha tocopherol, you can see alpha tocopherol just as an additive does almost nothing to protect against oxidation. This is percent inhibition. And mixed tocopherol is a little better, as I showed before. Mixed tocopherols tend to be a little bit better than alpha. But if you take these tocopherols and you actually feed them to the animal, then you get much, much better levels of protection. And the reason for this is because the biological system is actually taking that dietary tocopherol and putting it into the cell membrane. So when you look at the cell membrane of these fortified animals, their tocopherol levels in the membrane is much, much higher. So this is a much better way to protect these from oxidation. But probably even more striking is what they do to color. So by feeding, especially in beef cattle, by feeding those cows alpha tocopherol, you get quite dramatic increase in color stability. And this is still related to lipid oxidation, because what happens is that when the cell membranes in the meat start to oxidize, the aldehydes that are produced react with myoglobin, make the myoglobin more unstable and cause it to convert to the met myoglobin, which causes this brown color. So, in conclusion, so inhibiting lipid oxidation is obviously very important for quality to make sure you can maintain the highest quality, the highest flavor profiles that you can. It's also really important for food waste and food sustainability because, as I mentioned, that lag phase is going to determine your shelf life. So anything you can do to slow oxidation down will increase your lag phase, increase your shelf life, and decrease your waste. And then finally, there's just mounting evidence that these oxidation products are not good for you, and especially for people that have inflammatory gut disease, inflammatory bowel disease. So I encourage everybody to go home tonight, smell their vegetable oil, smell, I don't know if you guys use Crisco anymore. My mom used to have this Crisco that was in her cupboard for years that was obviously rancid. So if any of those oils smell, with the exception of olive oil's got all kinds of great flavors in it, so it's going to give you some smell. But if they smell painty or fishy, they're oxidizing. You probably shouldn't use it. Tocopherols are the major antioxidant found in most foods and are really pretty ubiquitous across the biological system. And because those biological tissues are used for our food, we find them in most foods. You can increase the stability of your food by adding tocopherols, but you can only do this to a point. Eventually, if you add too much, it will actually become pro-oxidative. And obviously, there's other antioxidants that you can use. So for the salad dressing, mayonnaise world, they still can't get away from EDTA because it's so effective. I think there's a lot of opportunities in the future to look at regenerating antioxidants like the phospholipids and the phenolics that have quite low reduction potentials, like myristicin. Quercetin falls in that same family. And then meat systems, antioxidants like tocopherols can't improve stability. But the best way to do this is if you're going to do it as an additive, add it into a polar carrier, or if you have the ability to impact the food chain, try to get those producers to supplement the animals with vitamin E. So thank you very much for your time, and I'd be happy to answer questions.
Great. Thank you, Eric. I've got a question that Matt had asked, actually. So I'll ask that, and then I'll introduce you as well, or you can introduce yourself, Matt, and just kind of set the scene within New Zealand. So is there any information about grass-fed meat having a higher tocopherol content than grain-fed animals?
Yeah, there's actually, you actually will get a much better tocopherol level on grass-fed, which is generally, I think, going to be very positive, but the grass-fed will also be slightly higher in unsaturated fatty acids as well. So that can make them a little bit more prone. But I think that the addition of you would get more tocopherol than unsaturated fatty acids. So overall, the benefit would be very positive.
Great, thanks. Matt, did you want to introduce yourself?
Yeah, not a problem. Hi, I'm Matt Miller. I work here at the Cawthron Institute. I'm a lipid chemist. I saw Eric speak probably a decade or so ago about lipid oxidation, and we've been catching up ever since. He is one of the world leaders in this space, and it's a real privilege to have him here at the moment. So, if any food industry out there is having some issues with self-stability or rancidity in their products, Cawthron's here to help, but we've also got Eric we can tap into over the next couple of months. So we're really keen to hear those problems, and we might be able to get some solutions.
Great, thank you. I've had a question come in. I've always noticed that New Zealand butter, if wrapped in paper, which mostly it is, has a dark yellow rancid layer all around the outside. The foil wrap versions or not. Would you cut off the dark yellow layer? Presumably it's rancid. I don't know if that's if it is actually rancid, or if it if it just appears that way from exposure to air.
Yeah, it's hard to say that if that's rancid, because sometimes you can see the color change that occurs as the emulsion breaks down. So like you'll see this in mayonnaise. If you leave mayonnaise out and you get some water evaporation, it starts to get a little clearish gray on the outside, and that's the emulsion droplets getting bigger. And so the same thing could be happening on butter. The place that you'll really notice oxidation in butter is you'll see the yellow color go away. Because when the lipids oxidize, they oxidize the carotenoids and they cause a bleaching of the butter. So if you left butter exposed to sunlight, your butter could eventually go entirely white. And if you cut into the butter, on the inside of the butter, it's still yellow because all the carotenoids have been oxidized on the outside of the butter because the light only penetrates so far. And yet the inside retains its butter. So it retains its color. So I would worry more about the lightening of the color with rancidity than the darkening of color.
Okay, thanks. And as a big butter eater in my household, I don't actually experience that problem because it never sticks around that long to change color.
Well, butter is much more saturated, so its tendency to oxidize is quite low.
Mhm.
But the cardinal rule of all oxidation at home is keep everything as cold as you can. So I keep vegetable oil in the refrigerator, huge in shelf life. And if there's a big sale on oil or olive oil or something, I'll put the oil in the freezer. And the same really prevent oxidation and does nothing at all to quality.
Great, that's really, really interesting to hear. Sorry, I think I don't know if it's my connection or yours, but we keep losing you, but you do keep coming back. I don't know if we've got any further questions from the floor. I don't know if Matt, if there's anything else that you want to add.
Not really. It's just been a pleasure to have Eric here. So it's great that he can do this for the centre.
Yeah, no, we're honoured to have another visitor and that you're able to share some of your experience with us. In that case, then I'll wrap up. So thank you so much again, Eric, for your time today. I know this is your second presentation today, so you're probably ready to give your voice a bit of a rest. And on behalf of the centre, we hope that you enjoy the rest of your trip to New Zealand, both the work aspect and the fun getting out and seeing the country aspect. Thanks to those of you who spent your lunchtime with us, and thank you for staying until the end. This has been recorded and will be available on our website soon under the events seminars section. So our next session will be advertised to you in a few weeks, so keep an eye out in your inboxes and we hope to see you next time. In the meantime, have a great rest of your week and a lovely weekend. Ka kite anō.